So now that we've looked at orders of reaction and the concept of reaction mechanism, the last step is tying the two together and looking at how can we use rate equations to help us evaluate possible reaction mechanisms. So that's the combination. So if we have this reaction here, NO2 plus carbon monoxide makes carbon dioxide and NO. Let's look at some possible mechanisms and some of the rules that are going to go along with figuring out whether or not the mechanism matches the rate equation. So the rate equation only depends on the rate determining step. So remember we said the rate determining step is the slowest step, highest activation energy. It determines the overall rate of reaction. So the rate equation, which is like the rate equals K times different concentrations, that's really just the mathematical way of describing the rate and the concentrations that affect it. So the rate determining step is really all that matters for the rate equation. The rate equation can initially be written where the rate equals the rate constant times the concentrations of only the species involved in the rate determining step, and where the coefficient of each species in the rate determining step ends up being the power of that species in the rate equation. So what do I mean by that? So if this is a possible mechanism, two-step mechanism, and I've starred that the first step is the rate determining step. So if this was the case, what would we end up with as a rate expression or as a rate equation? Well, if this is the rate determining step, then this is the only step that really matters. So that's what I'm going to focus on. And I'm going to say that therefore, because that's the rate determining step, the rate equals some constant, some rate constant. And then it equals, well, what's involved in the rate determining step? It looks like NO2 is involved, and actually NO2 is involved twice. So I could have written this as just 2 NO2. So in the rate determining, or in the rate expression, I'm going to write NO2, and then I'm going to write NO2 squared. So if this is the mechanism, and if this is the rate determining step, this is the rate expression or the rate equation that I get from that. I take the species involved in the rate determining step, I put them in brackets, and I put their coefficient, their overall coefficient, as their exponent, as their power. And that gives me the rate equation. Okay, that's for if the rate determining step is the first step of a reaction mechanism. If rate equations can't show the concentrations of intermediates. So if the rate determining step is not the first step, then it's going to be slightly more complicated, but still not that hard. So this is the same mechanism, but now I'm looking at if the rate determining step is the second step. So the rate determining step we're saying is the second step. So this is the only step that matters. So initially I would write down rate equals K, and then I'm going to put the concentrations of the reactants in the rate determining step. So that would be NO3. And there's only one NO3 in that rate determining step, so I'm going to raise it to the first power. Again, you don't really need to write the 1. Obviously, raising something to the first power is sort of implied without writing it, but it doesn't hurt to write it just to be extra sure that it's a first order reactant. And carbon monoxide is used once in the rate determining step, so I would use that one there. Okay, so this would be the rate expression. However, when we're thinking about the rate and how concentrations affect the rate, we don't actually know the concentrations of any intermediates. Intermediates are things that are formed in early steps and then used up later. So what I have to do is I'm going to have to get rid of this intermediate, and the way that I will do it is I'll sort of replace it with the things that formed it. So if I look at NO3, we know it cancels out of the overall equation. Well, what formed NO3 was this step. So the rate or the amount of NO3 actually depends on this previous step. So what I do is I'm going to replace NO3 with the species that created it. And so instead of having just one NO3, I actually have NO2 used twice. So I would replace NO3 in my rate equation with NO2 squared to match the step that came before it, that created the NO3. The CO is unaffected. CO is one of my reactants, So I'm allowed to just keep it in the rate equation. And so the overall rate equation now is this. K is the concentration of NO2 squared times the concentration of carbon monoxide to the first power. So depending on which step I label as the rate determining step, it has a major impact on what the rate equation looks like. If it's the first step, then you can just take those reactants, put them in brackets, and make sure the exponent matches how many times they're used in that step. If the rate determining step is not the first step, then any intermediates, which you might initially write in the rate equation, are going to have to be replaced by the reactants that formed the intermediate. And so it makes the difference between the rate looking like it's second order overall, if the first step is rate determining. If the second step is rate determining, in this case, we get a third order overall rate. So here are some more possible mechanisms for this reaction. If the first is the rate determining step, then this is the only thing that matters for the rate, and we'd get rate equals K and just NO2 to the first. If this is the rate determining step, if the second one is the rate determining step, I would initially write CO in brackets and O in brackets, but because O is an intermediate, I have to replace it with what formed it. And so in the end, I would get rate is K, and I'd get NO2 in brackets, and I would get CO in brackets both to the first power. So this would be the rate equation. So first, we're just looking at if we know the mechanism and we know the rate determining step, we should be able to come up with the rate equation that matches it. Okay. Going back to this first one, you may have said, well, how can NO2 be squared? How can it be second order? There's actually only one NO2 in the overall stoichiometric equation. It's kind of an interesting mechanism that's proposed here. It shows that the way the reaction actually takes place is that two NO2s collide, creates NO and NO3, an intermediate. NO3 then gets used, reacts with the carbon monoxide, creating CO2 and reforming one NO2. And so you can see that overall, for the stoichiometry of it, one of the NO2s cancels in addition to this NO3 as an intermediate canceling. So you do get the correct overall stoichiometric equation, and NO2 is involved twice in the rate determining step, so that's how it could be a second order reactant. Okay, so there's more things. Another common way that you could get reaction mechanism and order of reaction questions is once you have the rate equation, so you know what the rate equation is, then you are asked to evaluate different mechanisms, different rate determining steps to decide which ones are possible. Again, you're not saying this is definitely the exact reaction mechanism. You're just saying whether or not it matches with what you're given. So we'll do this one example here and then we'll call it. So if this is the rate expression, I've got NO is a second order reactant, H2 is a first order. If this is the first, if this is the rate determining step, then the only things that are going to show up in my rate expression, my rate equation, are H2 to the first power and NO to the first power. That does not match the rate equation. So assuming we've determined the rate equation properly from studying the reaction rate, then this mechanism does not match the rate equation shown above. If I do this one, the rate determining step means I would have this to the first and this to the first, but because N is an intermediate, I need to replace it with what formed it. These are the reactants that formed N, first and first. And so when I combine all these together, I would get NO squared because NO has been used twice. And I get H2 used once. And so that does actually match the rate equation. So again, this is not definitely how the reaction takes place, but it is one possibility for how the reaction takes place. And then this last one, just to double check, rate determining step was third. That would mean that this reaction mattered. The O is an intermediate. What forms O are these two things, but N is an intermediate. So what forms N is H2 and NO. And so in this case, the rate expression would have both NO and H2 being second order. So I'd have squared and squared, and that does not match the rate equation either. So based on mechanisms and rate determining steps, we can figure out rate equations, or based on given rate equations, we can evaluate whether or not mechanisms match those rate equations. And those are the types of questions you'll see on IB exam.